The projectile sampling distribution simulation is an innovative educational tool designed to engage students in hands-on data collection and analysis through the dynamic context of launching projectiles. This simulation not only provides a practical application of statistical concepts, but also brings to life the Central Limit Theorem, a fundamental principle in statistics. By allowing students to manipulate various launch parameters, the simulation offers a rich learning experience that bridges the gap between theoretical knowledge and real-world applications. The projectile sampling distribution simulation is built around the concept of launching projectiles with adjustable parameters such as launch angle, initial velocity, and air resistance. Students can input different values for these parameters and observe the resulting trajectories and landing points of the projectiles. The simulation then collects data on these landing points, creating a distribution of outcomes. The primary objective of this simulation is to demonstrate how different launch parameters affect the distribution of projectile landing points. By altering the launch angle, for example, students can observe how the distribution of landing points changes. A higher launch angle might result in a more spread-out distribution, while a lower angle might produce a more concentrated distribution. Similarly, changes in initial velocity and air resistance can lead to variations in the distribution shape and spread. The Central Limit Theorem is a cornerstone of statistics, stating that the distribution of the sample mean will approximate a normal distribution as the sample size increases, regardless of the shape of the original population distribution. The Projectile Sampling Distributions simulation provides a vivid illustration of this theorem in action. When students launch multiple projectiles and collect data on their landing points, they are essentially taking samples from a population of possible landing points. As they increase the number of projectiles launched, they can observe how the distribution of the sample means begins to resemble a normal distribution. This visualization helps students understand the abstract concept of the CLT in a tangible and interactive way. For instance, if students launch a small number of projectiles, the distribution of landing points might be irregular and not follow any particular pattern. However, as they increase the number of launches, the distribution of the sample means of the landing points will start to form a bell curve, demonstrating the CLT. This hands-on experience reinforces the theoretical understanding of the CLT and its implications for statistical analysis. The simulation allows students to actively engage with statistical concepts rather than passively receiving information. This interactive approach has been shown to enhance learning outcomes and retention of knowledge. The CLT and other statistical principles can be abstract and difficult to grasp. The simulation provides a visual representation of these concepts, making them more accessible and understandable. Students can experiment with different launch parameters and observe the resulting distributions. This exploratory approach encourages critical thinking and problem-solving skills, as students must analyze the data and draw conclusions based on their observations. The context of launching projectiles is relatable and engaging for students. It provides a real-world application of statistical concepts, helping students see the relevance of statistics in everyday life. The simulation introduces students to the process of data collection and analysis, which are essential skills in scientific research and many other fields. By collecting data on projectile landing points and analyzing the resulting distributions, students gain practical experience in data handling and interpretation. To implement the projectile sampling distribution simulation in the classroom, teachers can follow these steps. 1. Introduction. Begin with a brief introduction to the concepts of projectile motion, sampling distributions, and the Central Limit Theorem. Provide examples to illustrate these concepts and explain how the simulation will help students understand them. 2. Demonstration. Demonstrate the simulation to the class, showing how to adjust the launch parameters and collect data on the landing points. Explain the importance of observing the distribution of landing points and how it relates to the CLT. 3. Student exploration. Allow students to explore the simulation in small groups or individually. Encourage them to experiment with different launch parameters and record their observations. Provide worksheets or prompts to guide their exploration and data collection.